Hey everyone, welcome to this session on building smart contracts on Starknet. This is going to be a super interesting session because you're going to learn about how the smart contract architecture looks like, what are the different types of transactions, and you're also going to be building your own smart contract and deploying it on Starknet. So, in this session, we're going to be talking about classes and instances of smart contracts. What are the different types of classes? What are the different instances that are there, the anatomy of smart contract, what it looks like, what are the different components of a Cairo smart contract, and of course, there's going to be some live coding. Your teacher for today, that's me online. My name is Gyan Lakshmi. Everyone knows me as Gyan. I'm a developer advocate at the Starknet Foundation. I'm born and based in India, Bangalore, India, and I can speak English, Hindi, Tamil, and French. Yes, I learned French as a hobby. And if you want to reach out to me for any help, feel free to reach out to me on Twitter or Telegram. Both of my handles are the same, which is @. Don't get confused between this spelling and this spelling. This is my official spelling, but this is how people call me. Okay, perfect. So, yeah, this is going to be a great session. I hope you enjoy and have the most fun. Take it slowly, pace yourself, and this is going to be a very interesting session and a very foundational session for you to learn about Cairo smart contracts itself. So, yeah, best of luck and have fun. The first session is just all about understanding how the anatomy, how the classes, the contract classes and instances would look like. Let's quickly see this. I think you might have seen it in the previous session, but just to give you a quick recap, Cairo is a provable programming language, and we write smart contracts for Starknet in this provable programming language called Cairo. The syntax of this programming language is very similar to Rust. Since you're already doing Starklings and stuff, you might see all of those similarities. If you compare it to Rustlings, it's like quite similar. But you will see some small but noticeable changes when you're writing using this programming language to write a smart contract. So please make sure that those small changes can be very significant messages to the compiler, right? So that's something you want to make sure that you're keeping track of. Cairo programs compile to Sierra, which is a safe intermediate representation. We will try to take a look at some Sierra files, but of course they just look like hexadecimals and stuff. So we will take a small example of that as well. And the sequencer compiles Sierra to safe Chasm. So Chasm is Cairo assembly, which in the previous stage of Cairo, which was Cairo 0, the Cairo smart contracts directly used to compile to Chasm. It had its own drawbacks and stuff like that. But now there is a safer version called Sierra, and then it compiles to a Chasm, right? The Chasm is the contract that the assembly which is actually deployed on Starknet. Now, in this one, like I mentioned, in the latest version of Cairo, the failed transactions are included in blocks. So in the earlier version of Cairo, these failed transactions were not included in blocks, and because of that were the cons that I was mentioning, like there's a potential of like DOS attacks and stuff. And the Sierra is the one that enables this to happen, the failed transactions. So being able to have a safe intermediate representation is what enables you to be able to add failed transactions into the blocks. And because of the failed transactions are added, the sequencer is always compensated. So you can't actually attack the sequencer and keep it bogged down. And we don't see the DOS vector as we used to see in Cairo 0. So you don't have to worry about Cairo 0. But I'm saying that we get questions sometimes like, why Sierra? Why do you have an intermediate representation? This is exactly why we have it. We want the contract to compile into a safe intermediate representation so that even if the proof is invalid, it becomes a failed transaction and we are able to include it in blocks. And Chasm is Cairo assembly. Of course, from the Chasm, we generate a validity proof, which then gets the proof goes to the verifier, and the verifier verifies the proof at the Ethereum layer. We'll see that in just a bit.
There's a question from Leon. What exactly does it mean to be safe in the case of Sierra and Chasm?
So the safe intermediate representation is kind of ensuring that the way your Cairo smart contract compiles, um, so it adds certain nuances to the way the compiled contract can be represented. For example, in the previous versions, there was no branching or anything that allowed certain conditions to take place. You didn't have the ability to have something like, if something happens, then take this particular action, else take this particular action. But now with Sierra, we have the ability to determine if the particular path that you are going through is correct, then your proof is valid. And if the path is incorrect, then the proof that you're generating is invalid. So this is one example of how you bring in safety. But there are a lot of like these other kind of nuances that that Sierra brings in when it comes to like types. I don't want to type safety is the wrong word, but basically being able to have a program that can generate a result that could be either valid or invalid. So Sierra brings you that ability to do that. Did I answer your question satisfactorily? David, maybe you want to add something?
Just maybe in a short sentence, that safe means that if the transaction execution fails, it can still be included in the block and can still be proven. Before it was not possible, so failed transactions were just pretty much ignored.
Yeah. Okay. So now, when you think of Starknet contracts, what are the different things that you get? So there are two things that you will see. You will notice when you are trying to work with a contract. So there are two steps to actually getting your written contract to on-chain. So the first step is called declaration, right? So if you don't declare your contract, then you will not be able to deploy your contract. So this is the first step. That is, you declare your contract to create a contract class, right? So this contract class consists of the Cairo code that is compiled to Sierra, the ABI, that is, which are the functions that are accessible, and it generates a class hash of your contract class, right? So the contracts that we write, the smart contracts that we'll write in Cairo, the first step that we do with them is to declare those contracts and generate a class hash of those contracts. So every time we modify the code, basically the the class hash changes. So this is the first step that you will always do with your smart contracts. Now, the second thing, the contract address that you find, like say on Starkscan or whatever, that is actually a contract instance, which has its own storage, the associated class hash that you declared in the previous step, and it has its address, which is what we call as the contract address. So when you deploy a contract on Starknet, you are actually deploying an instance of the contract on Starknet. But in order to deploy an instance, you need to declare the class and have a class hash for yourself. So I have another diagram that kind of explains it nicely. That is, if you have a class hash, say 0x123, you can deploy multiple instances of that contract, each of them with their own storage, with this particular class hash, and having their own distinguishable contract address. So you can see here that the contract address is 0x981 and another contract address is 0x248. So these both are instances of this class hash. And there is another example with the same, which is you have another class hash and you can deploy multiple instances of this. So this is very useful because I know you might have, if you come from Solidity background or just object-oriented programming background, you might have heard of factory patterns, right? Where you have a top factory which can help upgrade contracts, or which can help call other classes, keeping the functionality the same in the oops. So this kind of helps make the upgradability quite easy. And I'll show you an example towards the end if we have some time about the factory pattern and stuff. But just remember two things. So first, you have to always declare your contract to get a class hash, and you have to use that class hash to deploy an instance of that class hash, and then you get your contract address. Okay. Now, the next thing is, how do you alter the Starknet state, right? So once you deploy a contract, you can basically read from that contract. So these read calls are free, or you can write to the contract where it's a transaction and you have to pay some gas fees. So read is more like call functions and write are invoke functions. So let's see again, what are the different types of transactions that you can do. The first one is declare. So you declare and you get a class hash. The second is if you have to invoke a particular instance, right? So if you have to invoke a function, you have to make some changes, or you're going to write in the contract. So that's going to be like, you're interacting with an instance of the contract. And the third type of transaction is deploying an account. So every account in Starknet is a smart contract account. So deploying an account is also a type of transaction. And even over there, you are deploying an instance, right? Because you are generating a contract address. That address basically becomes your wallet address that you work with in Starknet. So these are the different transactions types that we have on Starknet. And let's take a quick overview of how this would kind of look like. Just ignore this mempools. It's not the same as Ethereum mempools. Just think of all of these as transactions. So the sequencer receives the transaction. And over here, you basically, the sequencer is the one responsible for creating blocks. And it creates the blocks, and then you get this L2 block. And you create a trace and send it to the prover. The prover will create the proof, and it basically it runs and proves the Starknet OS. Then it sends the proof to the verifier, the generated proof, and the verifier will verify the proof on Ethereum. So you see this is the L1, this is L2, and then you have Starknet core contracts that are also for interacting with the Starknet OS. And I think what is missing in the piece is like you have some data backup and like data nodes and stuff where you can create the backup for your L2. So this is like a simple way of kind of looking at how transactions work on. So when you deploy a smart contract also, they are going through the same process. What can you do with all that you learned? That is Starknet smart contracts. You can build on-chain games. You can work on things like Giza, which is verifiable neural network execution. Please don't ask me what this does because I have no clue. But I have some ML background, but I don't know what is happening at the intersection of ML and blockchain. So, but whatever is happening, it's like really cool cutting edge stuff. App chains, of course, we have Madara trees, that whole narrative of building your own app chain, being able to customize things as per your application and your users' needs. We have a ZK EVM project, which is Kakarot, which is writing EVM opcodes in Cairo. Very, very interesting. And they are just about to launch, I think, mainnet. They are doing a lot of rigorous testing, stress testing, and all of that. And yeah, a lot of other cool stuff, right? This basically explores the world for you to build anything on chain, but with being able to pay lesser gas fees and not worry about like scalability issues. So smart contract anatomy. So now we are going to start a little bit into like looking at different pieces of code. After these slides, there's someone who raised the hand, David. Two people have raised their hands. Okay, so for all of the next slides, you'll just be looking at pieces of code and understanding what these pieces of code look like, what these pieces of code mean. A compilation of all of these pieces of code is just your smart contract, right? So I've just put different pieces in different slides, and then it all comes together and becomes a smart contract eventually. So the first thing is, this is how a bare minimum Starknet smart contract written in Cairo looks like. So what I'm saying is you can't just write something like mod counter contract without any of these annotations and just open close braces. That's not a bare minimum contract. A bare minimum contract will have this annotation, which is your Starknet : contract. This is because, like I mentioned earlier, Cairo in itself is a provable programming language. So when we are writing a smart contract for Starknet in Cairo, we have to let the compiler know that this is a smart contract. So we have to annotate it as a Starknet contract. And Starknet contracts, smart contracts, are Cairo modules. So when you want to write a contract, you say mod, which is the module, name of the contract, open close braces. And then you have to have a storage defined. So a smart contract must have a storage defined, even if it is empty. So now this is your bare minimum Starknet smart contract written in Cairo. Let's go to the next one. Now we're going to keep on adding elements to this bare minimum smart contract, right? The first thing we are adding is, of course, a variable inside the storage. So we have a storage variable called counter. Now, storage variables are variables that can be accessed, that can be modified, that can be written to, that can be read from, and you can access these storage variables throughout the contract. So now the first thing that we always have is a constructor. So a constructor is like an initialization function. So you have to annotate it as constructor, and the same way for storage, you have to annotate it as storage. So you add it's nothing but a function, the constructor. So the keyword for that is fn. For every function, the keyword is fn. Then it's best practice to name it constructor, right? It must be called constructor. And then you have arguments of the constructor that you see here. One is called ref self colon, the type of the argument. The second name of the argument is initial counter, and the type is U32. I'll talk about what is this ref self in a bit. So these are arguments to the constructor. And then in this constructor, we are basically writing some type of value, which is this initial counter, to this storage variable, right? And we are saying that take this storage variable within my contract and then write to it this new value. Okay, this is what this is doing. And the constructor is only called once when the contract is deployed. And if you don't have anything to initialize, then you can just omit the constructor. It's not something that you need to have mandatorily, right? Simple. So the next thing, of course, once you have your storage, once you have your constructor, the next you're going to start adding functionality to your contract, right? So we come to functions. So to write a function, you use the fn keyword, name of the function, then you send arguments within the function, right? And if you want to return something, if you want to return a variable, your function returns a variable, then you use this arrow symbol and then write the type of the return variable. Then within open close parenthesis, open close curly braces, you write the logic of your function, right? This is a simple way to define a function. Now, but the topic of this is not defining a function. It's called exposing functions. What does that mean? This means that how can you access your contract functions? What are the different things behind being able to access your contract function? Now, the first and the foremost important thing is that whenever you are having your main implementation block, right? So in Starknet smart contracts in Cairo, you have this concept of interfaces and implementations. Interfaces are defined as traits, right? Which in English means characteristics of this contract, which we will also talk about in just a bit. But each of these interfaces define what is going to be the blueprint of this contract. That is, what are the different functions that this contract is going to have? What is largely the logic of this contract? And then you implement those functions in an implementation of that particular interface, right? And this particular implementation has two functions in this case, which is a get counter and the increase counter. Now, for this implementation block, if you want these functions to be able to be called external, then you have to add this annotation called ABI embed underscore V0. This is an important annotation that tells the compiler that this particular implementation block can be called externally. So this is the first thing that you need to understand. Now, the other different, so now automatically you're exposing these functions to being able to be called externally. Okay. Now, what are the other nuances of calling a function? Either a function can be a read-only function where you are just reading the storage variable, for example, in that function. So let's see what are some nuances defined in the function in order to do that. So when you have a read-only function, that is a view function, you will see this format, which is self and then colon at contract state. So this self says that the contract state, so I want to access the contract state of this particular contract, which includes your storage variable, right? But I don't want to manipulate it. I just want to read it. So I'm going to access a snapshot of the contract state. So the at refers to a snapshot. So the read-only functions take a snapshot of this state as a parameter, and then you can read the value. So for example, counter is the storage variable. You can read the storage variable using self. So in every function that you define, self should be the first mandatory variable, because using self is how you can access the contract state of that function. So you see in every function that you will see self. However, you will see self depending written in a way whether it is a view only contract or whether it is a write state, whether it is a view only function or whether you are actually doing some write. Now for the view only, we saw that the self is just a snapshot of the contract state. Now in this case, which is where you are writing something, you are using a reference, right? So you're taking a mutable reference to the contract state. So you see, you are saying that this self is actually a reference, and you're taking a mutable reference to the contract state, which allows you to perform a write operation. If you remove the ref in this case and you try to write it, you will not be allowed, right? So there are three takeaways from this particular slide of exposing functions. One is you want to expose all of your functions within an implementation block to be able to be called externally. So you need to add an ABI embed annotation. Another is, now we come to the function themselves. If the function is read only, it's only doing read operations, you can have a self parameter, and this only takes the snapshot of the state as a parameter. So you will see the at. Or if you want to write, then you have to take a reference, and this takes a mutable reference of the state. Of course, this costs gas, and this is free. Okay. Why do we have this syntax? Because it is for better maintainability, and then you get a compiler error on type mismatch. So it's good. Plus, it is important because you deal with a lot of state changes in blockchain just in general. And it is like you see a lot of hacks happen because there isn't proper access control, or there is a lack of understanding of how which functions, which part of code can access which other part of code, right? So this kind of gives you a better understanding of what is read only, what is external or write, and things like that. So like I mentioned, in order to communicate to other people that what a particular contract would be doing, right? You actually write an interface, right? An interface is like a blueprint of a contract, that what are the functions will this particular contract have. And you can also see like the arguments, what are the type of functions, are they view functions, are they write functions, or what, right? So interfaces in Starknet require this annotation, which is hash Starknet interface. And they are declared in the form of traits. So you have to use the keyword trait. Then we use I to denote that this is an interface, right? So we have I, and then this is an interface for the counter contract, right? That this is what we are writing. So we have the trait called I counter contract. And within this is basically what is the generic object that this trait is going to act upon, right? So this trait is basically telling that these are the functions that are part of my program, and these functions are going to act on a particular type of variable. Got it? So that in this case, we are keeping it generic. So when we implement this trait, we can tell what type of variable is it upon which the functions of this trait will act. So we give that type of variable in the implementation. So we have this trait, and then we have a generic. Okay, this can be whatever. This can just be T also, right? I am used to just writing as T, but because just to let you know that we are actually going to modify the contract state, we have written it as T contract state. So you might have commonly seen it in Rust and other programming languages as just T. So it doesn't matter. If it is T here, it should be T here, and it should be T here. That's it. Right? It's a generic variable that we're representing. Within this trait, we are telling that there are going to be two functions. One function is called get counter. So we are just going to give the blueprint of the function. There's no implementation of this function. So we're going to say that the function name is going to be get counter, right? This is not taking any other arguments except self argument, right? That means the self argument is required to access the contract state. So self, and it is going to take the snapshot. It's not going to write. So it's just going to read. And with arrow, whatever comes after is the return type. So this is a type of variable that is going to return. It's going to return a U32. And the second function is an increase counter, which is a reference, like basically you're giving a reference. So you're going to be having a mutable access to this type of variable. This also tells us clearly that this is a function which is going to aiming to write something. So now we have the blueprint of this. Once we have the blueprint, within our contract, we can implement how we want, what is the functionality of these functions. So this is where we are saying that we are going to implement the counter contract, right? The functionality now. And we say super because the interface is defined above. We'll do this in the in the counter workshop as well. So most part of the code is here already. So we have this. So what we are doing is the I counter contract is the interface, and now we are saying that we want to modify the contract state. So we are giving the contract state as the instead of the generics, right? Instead of T, we replace by contract state, and we're going to implement the functionality that the blueprint gave us. And the functionality has two functions: get the counter, which just returns a U32, and increase the counter, which is doing some, operations with. So quickly, this one I have already explained. So these are called explicit interfaces, where you define the interface and then you implement the interface. So everything you're doing explicitly. You're saying that here is the interface, this is the blueprint, and then you are going to implement the same interface with the functions that you have defined inside the blueprint. Okay. So that's why they are called explicit blueprints, and then so explicit interfaces. And then you have I already shared this ABI embed for enabling the functions to be called externally. However, you can also have something called as implicit interfaces. These implicit interfaces can be of two types. One is you can have an implicit interface where you don't have the interface itself is not written above. So you're saying that generate this trait for me. That is, I'm writing the implementation. You just generate a trait for it internally. Okay. So this is more like an implicit interface. Now, in this case, we have mentioned that these functions should be external, and we have to also mention the ABI. So in order for these to be called externally, there is another way to do the same implicit interface where we don't mention this ABI per item, nor do we mention these external V0. Imagine that these three lines are gone. Okay. The orange lines, ABI per item, external V0, both are gone. But we have the generate, and we have some functions that we are having inside an implementation. These will be automatically private functions and internal functions. So you can't call them externally. So if you want to have some internal functions that you just want to want to call from inside, then also you can create an implementation and add the generate trait annotation to it. So it will automatically implicitly generate a trait for you. So these are the two differences. I'm also gonna quickly run through events. So of course, in order to communicate with the world what is happening in your smart contract, you want events, right? And for events, you have to think of events as having two types of structures. Okay. The first is an enum called event that you have to define, and you have to tag it as an event, right? So that's when the compiler knows that you are now defining some events for your contract. You're going to define some events for your contract. So you say that I want to create events for my contract. So you create an enum called event, you tag it with event, and then it has to derive this property that it's a StarkNet event. So this StarkNet from which the event is being derived is already published as a part of the core like Cairo libs. And you are basically deriving that event property for this particular enum, right? So drop is another property so that it can be deleted. So it can be dropped. That's the idea. Now, the first part of this is that now inside the enum, you declare the name of the structs, which are actually the events. So you declare the events inside your enum. So this is the name of the event and this is the type of the event. So both are the same in our case. And as you keep writing more and more events at the moment, you will keep them as the same name. So now for this, so you can define multiple events inside this enum. Okay. So for example, ownership transferred, ownership regained, something triggered, transfer triggered, or something like that. You can define multiple events inside this enum. Now, in order to define what will be emitted as part of this events, you have to create a structure. So the events themselves are always defined as structs. So these structs also have to derive the event property from the StarkNet lib. So you're deriving both drop and event property for this particular struct. And then you give the parameters that this particular event will emit. So for example, this ownership transferred event is going to emit a previous owner, right, of type contract address, and the new owner of type contract address. So who was the previous owner and who was the new owner? Now you might see a small additional thing called the key, which is basically to index this event faster. So when you're querying the blockchain and you want to do a quick search, right? So this key will allow you to index this event faster.
So that's the whole purpose of adding this key to it. Okay, yeah. So this is basically, you have to remember that an event requires two things. An enum called event, within which you will declare what are the different events that you want to have. And each of these events are actually defined as structs, within which you will write the parameters that you want to emit. Okay, I think this is probably around my last slide or something before we go to hands-on. Now, the last thing that we're going to talk about is how do you call one contract from another contract, right? So calling one contract from another contract. You can do that using this concept called dispatchers. So in Starknet, in Cairo contracts, you can dispatches are automatically generated from interfaces. So for example, when you're writing this interface called iData, which has two functions, get data and send data, right? This is a blueprint of your contract, right? There is automatically a dispatcher that is generated for it as iData dispatcher. So there are two dispatchers that are generated. One is iData dispatcher and a trait for it, which is the iData dispatcher trait, right? So this is automatically generated from interfaces. So we have to use these dispatchers to be able to call the external contracts. So in this case, for example, we have a contract called my contract, which needs to call some function within this iData state. So think of this as like there's like another callee contract, right? So what we can do is we are going to get the iData dispatcher and the iData dispatcher trait, right, of this particular interface that we need to import into our contract. And the way we call it is like this. So this is the ABI embed V0. That means this function can be called externally, right? And we are taking two parameters, the contract state. So we are not modifying the contract state. And we are taking a data address, which is the contract address of this particular contract, right? And what we are going to do is we are going to call this iData dispatcher with this particular contract address. This will call this particular contract and give us the address, for example. So this will give us the contract instance of this particular data contract. And using this contract instance, we can call the function within this contract. So using a dispatcher, the function is executing with the storage and context of the targeted contract, right? And then we have another type of dispatcher, which I'm not going to go into, which is the library dispatcher. So you use this to call a function in a stateless manner using the storage and context of the current contract. So let's not worry about this. For now, we will work with this, which is also going to be part of your homework. So the main things that you have to remember, the one main key thing you have to remember is whenever you're writing an interface, there's going to be an automatic dispatcher that is generated for that interface. You can directly call that particular contract, which implements that interface. As simple as that. So this is how you call an external contract from within another contract. Okay, now this components is slightly new. It's just like, think of these more as like libraries or key components of for modularity. So the way components look, it's very similar to the way a contract looks. But components are for the purpose of bringing modularity. So they can contain functions, storage, and events. And they are more like modular add-ons that you can use in your contract. So for example, think about an ownable contract, right? It is something which is very commonly used in Solidity, like to check whether a particular contract address is actually owner or not. So imagine that if you can publish that ownable contract as a component, you can use that component within your contract and call certain functionalities. So that's the whole point of like components. Components become part of the contract's bytecode. So you basically use the components within your contract and they become part of your bytecode. So you can publish components, right? And it can be implemented in multiple contracts. So this is a good example, but it doesn't have how to use the component. So I'm going to share my screen and show you a very quick example. So I want to show the components example from here. Yeah, okay. I'm also going to share the link with you. We don't have to worry too much about it. It's not part of our counter contract anyway, but it's just good to know like that this modularity, idea exists. So instead of marking it as a Starknet contract, you mark it as a Starknet component. You see it has very similar sort of vibe as your contract. So it has the interface, and then it has, it's defined as a module, and it has a storage. This one has an event, right? So you see that this has an event, and this is the struct, that is the event itself defined as the struct. And it has an implementation. It has two implementations. One is an embedded implementation, and one is a implicit implementation. And the way you use this component in a contract, this is the piece that was missing in that screenshot, which I want to share, which is you have your contract, and then you kind of just take the implementation from the component, right? And this is the switchable component. It had the this particular implementation, and then it has this another internal implementation, which was this one. So you see there's one implementation, there's another implementation. We are taking both of these implementations over here, right? And we are just calling the functionality. That's it. So this is the way you can use the components. So you can publish this as a component, and then you use the implementation of this. There is more deep dive on the Cairo book as well, but we are just going through, like sort of just breezing through these concepts, so you are familiar that, okay, like this exists. Whatever you saw until now can be useful now that you start to write the code. The first and the foremost thing that I want you to do is, I've shared a GitHub link that please go to that GitHub link will lead you here, the GitHub repository for the counter workshop. Please clone this repository onto your systems, please. So you can copy and then like, let me go to my terminal. Okay, some random stuff open. Okay, so I would suggest that you kind of create a new directory for yourself. So let me actually do that. I'm going to Basecamp cohort 9. So within Basecamp cohort 9, I'm going to clone this. You don't need to fork it. You can just clone it, because you're not going to submit any like PRs or something. So you don't need to fork it. Okay. And also we would need these installations already installed. So Robert mentioned that he has already done the installation in the previous session. So you should already have ASDF, you should have SCARB 2.6.4, you should have StarkNet Foundry 0.23.0, and the Cairo 1 extension for VS Code. So if you would like to use Docker as well, you can use Docker. So I'm going to do the without Docker version, but everything that you're doing should also run within the Docker as well. However, this repo already comes with the test cases. So you would know whether the code that you wrote is actually correct or not. So this is going to be a very simple, like follow along workshop. Literally all the instructions that you need are here. I'm just a mic for these instructions. That is, I'm just going to repeat these instructions that are already here and maybe talk a little bit about why we are doing what we are doing. A major part of whatever we are doing, you have already seen how that code looks like on the slides, right? So now you have some sort of recall value that you want to get from there when we are solving these problems, right? Hands-on. So that was the reason why we have slides. We can try other sort of things as well later on. But yeah, so let's go for the workshop. So now I have my terminal and I have this the GitHub opened as well. And I'm just going to follow the instructions step by step. Okay. The way we are going to do this is we are going to look at, so the first step I'm going to do with you. And then the next step onwards, right? What I'm going to do is I'm going to read out the step. I'm going to give you some hints which are already there over here. And then I'm going to tell you that, hey, I'm going to wait for you for a minute or two until you try to attempt to do this step yourself. And if you fail or you're not sure how to attempt this step, then I'm going to just come back to it after 2 minutes or so. Okay. We're going to do it that way. I'm going to let you attempt the steps, and then I'm going to get you into the, so the next, as we keep going, you will become faster and faster. And the need for me to just attempt this itself will kind of go away. That's the objective, right? So let's do the first step together. Okay. So we're going to do, we are just copy the git checkout B step 1, which means that we are branching to a different branch. Okay. So I'm going to clear here, and I'm also, after I clone the repository, I did CD counter workshop. Okay. So I'm inside this repository now, and I'm just going to check out and move to the first step. Okay. This is a branch, which is our first step. Okay. So let's see first what we have inside this branch. So I'm going to open my code editor. I have a VS Code. I'm also gonna see the folders here. You can see that there are some Git folders, never mind. There's a tool versions which expects you to have a specific version of the different toolset that we have, which is mentioned in the GitHub as well. Okay. There's a README, of course, and then you have a scripts folder and you have a Docker Compose for if you're doing it via Docker. Okay. There is nothing else over here as of now. We are at step 1, right? And then what I'm going to do is I'm going to open this in the code editor just in case. I'm going to do this for all the steps to see, just again to, take a look and stuff. We saw the files, right? The tool versions that we need are StarkNet Foundry 0.23.0 and Scarp 2.6.4. Okay. So I'm hoping you all have this. Many of you have raised your hands. Okay. So now what is the goal of this particular step? The goal of this step is we need to initialize the project structure within the clone repository by using the Scarb package manager and enable compilation of StarkNet contracts. So there are multiple things to this requirement, okay? When we initialize the project with Scarb, so the first thing that we need to do is initialize the project structure using Scarb. So Scarb is a package manager which is used to manage your StarkNet smart contracts. It is used to actually manage Cairo individual Cairo programs as well as StarkNet smart contracts. For us, we are now looking at StarkNet smart contracts. So if you're familiar with Rust, then Cargo is a package manager for Rust. Similar to that, Scarb is your package manager for managing your StarkNet smart contracts, Cairo smart contracts. Okay. And because it is by default a package manager for Cairo, you have to enable the compilation of StarkNet contracts by adding some things to the configuration of this package manager. Okay, this is what this goal is. It's asking us to achieve this goal. So what are the specific requirements? Specific requirements are when we initialize the project with Scarb, we have to name the package as counter and we have to do it within the clone repository. Okay, so we have all the hints now. We are within the clone repository. Now let's see what it means to initialize a project with Scarb. So how do you know what are the different things that Scarb can do? You can just type Scarb help. Okay, we see that Scarb has different commands like we can add, remove, build, check, cache, clean, and all of that. And then we come to init, which is what we want to do because it's asking us to initialize. But there is a catch to it. We need to name the package as counter, right? So let's go to Scarb init and ask for help. So there is an option called name that we can add, which sets the resulting package name, right? And it defaults to the directory name. Remember that the directory name is counter workshop, but the instruction for us is to name the package as counter. So let's do Scarb init --name and count. Okay, we get some warning that the git ignore file already exists. Right, we are trying to initialize this. So it says that git ignore exists. I don't have to worry about it. Now it says it has created a package. We have already opened our code editor. So let's see what that means, okay? So now in our counter workshop code editor, we can see that few more folders have been created. We have a file called scarb.toml that got created for us. We have a source folder that got created. Initially, we only had scripts and we had this README and all of that, tool versions we had. So inside the source, there is a default file called lib.cairo that has been created for us. And this has the code of a Fibonacci series, if you're familiar with that. This implements a Fibonacci program and there is a test case for this program. So this already lib.cairo has a default code and if this source folder has been created for us, has been generated for us. Okay. So far, so good. So we have gone through the first instruction. So whenever you initialize a new project with Cairo or with Scarb, you will get a source folder with the lib.cairo, which is the default file, and it will have the pieces of code in it. So you might have seen, I think even Starklings uses Scarb. So you might have seen that you have different files and then there is a lib that encompasses all of them together. And then you have a scarb.toml and all of that. Okay. The scarb.toml is actually a configuration file, which we will see now. Okay. So it says that create a new Cairo file under the source directory named counter.cairo and add the following starting code. Okay. So I've copied this starting code now. Okay. So this is the one that we're looking for. Under source, it's asking us to create a counter.cairo and copy this code. Okay. I've copied it now. Now in the lib.cairo file, remove the code and define the counter module. So what we are going to do is we are going to remove this and we are going to say module counter. That's it. So whenever you define a new Cairo contract that you want to add inside your source, you can have multiple Cairo contracts here. But the entry point for this to be built, when Scar builds it, it looks for all of the files at lib.cairo. So if I just had counter.cairo separately, and I didn't mention the counter module here, and I still had the Fibonacci code, it would just build that Fibonacci code. It will not be able to find the counter contract. So that's why the best practice when you write code is you can have separate files which are for your different logics, and then define the modules in the lib.cairo. So when Scarb is building, it will be able to access these modules, right? It works the same when you are working with Cairo as well, or Starknet smart contracts written in Cairo. Okay, so now we learned how to basically create a Scar project, how to create a new Cairo contract within our source, and how to add that as a module within the lib.cairo. And now they have asked us that initialize the project structure and enable the compilation. So let's try to build it now and see if this works. Okay, I'm going to save this. I've saved this and I'm going to try and build it. Okay, so it builds. It gives me a target. Okay, however, there are some more things that we need to do in order to be able to get some type of in order to be able to get a chasm, right? To be able to create that assembly file that we can actually deploy. So in order to do that, we can check out the hints where we say that to enable Starknet contract compilation, we need to add a target as the Starknet contract. We need to specify the Cairo version in the scar.toml, right? So let's go over here. Let's look at the scar.toml. So we have to specify the Starknet version under dependencies. So we're going to say that we need version greater than 2.6.3. And we also need to provide a target as the Starknet contract. So this is the way that this Scar will be able to compile this particular contract, this particular piece of code as a Starknet smart contract. So we have to provide the target as Starknet contract. And then what will be the version of Cairo? So we say that Starknet greater than 2.6.3 is what we're looking for. So we have 2. Greater than or equal to. So we can check this with the Scar version as well. And so all of these instructions we have cleared. That is, check out the Scar init command. So this was the hint which, I did it for you directly so that you get the flow with me for the first step. So we have the Scar init command, Scar init -- name package name. And you can also refer to the cheat sheet for different type of Scarb commands. You can also do a Scarb help as I did. And then we need to enable Starknet contract compilation. So we need to add the target as Starknet contract, which I've added over here. And we can specify the Cairo version in the scar.toml. So this is the version that I have specified. Now, again, if I do scar build, it should. Okay, perfect. So now that you can see that after I did the scar build this time, it has created a Starknet artifacts.json, which has the contract related artifacts, right? So at this point, we don't have anything much because the code itself doesn't have much stuff. But you can see that now after adding that dependency, I'm able to get the artifacts related to the contract itself. Otherwise, it was just compiling the Cairo code as the Sierra. So with step 2, what I'm going to do is I'm just going to read this. I'm going to switch the step 2, read the goal, and give you some time to implement step 2 yourselves. With the next step, again, you just need to copy the step command. Okay. And I'm going to again paste this here. Okay. So now we switch to the branch step 2. Okay. For step 2, let's quickly see what is the goal. For step 2, the goal is to add SN4 as a dependency within your scarb.toml. Okay. Now you know how to add dependencies on scarb.toml to allow execution of tests with Starknet Foundry. So Starknet Foundry is a framework which helps you write tests for your Starknet smart contracts, right? In Cairo, the same programming language. So we are going to add that particular SN-Forge as a dependency within our scarf.toml. So the requirements for to complete this step is in your scarf. Declare the SN-Forge _ SCD package as your project dependency and enable Chasm contract class generation. In your scarf.toml, define a script named test to be able to run SN-Forge test command. And in your scarf.toml, set your edition to target 2023_01. And once you have completed these steps, if you run scarf test, this will be successful for you. So how to do all of this? You can find it all in the hints. So when you are trying to add this SN-Forge STD package, you can find it from the StarkNet Foundry documentation, how you can add that package, right? And remember to specify the version of Foundry that the project currently uses. That's a tweak you have to make from the example that's given here. Then how do you add the script? You have to add a script which is test pointing to SN-Forge test. For that, you will find the documentation in this other link. And then the edition 2023 is a type of configuration that targets the general version of Cairo Prelude. So what the Prelude is, you can find out more about this, but you don't have to go too much into it. Just make this change, add all of this, and you should run scarf test. It should be successful. Okay. This is the step that you have to do. I'm going to give you 2 minutes to do this. Okay, so I have branched to step 2, and I'm going to do these same things as I mentioned I would. Okay, so I'm going to go to these. So there is the dev dependency. This is right here, right? This is what it asks you to add. I'm going to add it as a dev dependency itself. Okay, so I'm going to say here, because we are using version 0.23, I just need to make that small change. Okay. And then for the next step, it says that I need to change the, okay, I'll do this one first. Need to change the edition. So that is 2023_01. It also says actually that I need to enable Chasm contract class generation. So I can do that under this target. So I say Chasm is equal to true, right? So it will generate Chasm files now. And the last one thing is define a script name test. So for this, you can check the scripts. How do you define scripts? So let's scroll down. So here it says scripts. Okay, I'm going to take this. I'm going to add scripts. Define a script name test, which should run SN-Forge test, this command. Okay, so I've saved my file. Specify the version. Okay, so I have done this. That the project, specify the version of StarkNet Foundry. So I've done this. Refer to this for doing it. I also refer to the scripts, how to add, and then this edition. Okay, now I have to do scarf test to check whether everything is correct or not. So let me do that. Okay, so now it says, okay, like it compiled it, and then it just ran, counter test saying that it works, right? So, and then test the SN-Forge, whether dependency is there or not, it works. Okay. So now if you go to your setup, if you go to your folder, you can see that there is a SN Foundry cache that got added because I added the SN-Forge as a dependency, right, over here. So it is, you can see that the dependency is coming from Foundry, which is the StarkNet Foundry, which is used for writing tests, right? So you see that there is a cache folder that got created for it. And then in this step, you will also notice that a new folder got added, which is called tests. Within tests is where we have test_step.cairo. So you can see that a test has been written using SN-Forge to test whether SN-Forge has been installed correctly or not. And because we passed this assertion, we got a successful message on our terminal that yes, your tests have passed. So you see that this new folder got added in this step just to check whether we have added the testing dependency correctly or not. So let's go to step 3. Again, for step 3, I'm going to give you 2 minutes. After step, maybe I'll have to stop with step 5. I'll see. Let's see. Okay. Let's go to step 3 and let's move to step 3 and see what step 3 requires us. With step 3, we need to implement the constructor function to initialize an input number and store a variable named counter within the contract. Okay. So this is easy peasy now. For you all, this should be easy. Just look at the counter contract. Okay, you already have a storage struct defined. You don't even have to define it separately. Why? Because a bare minimum contract needs a storage, right? Now, as per the requirements, you need to store a variable named counter and its type should be U32. Okay, simple. The next is you need to implement the constructor function that initializes the counter variable with a given input value. Now for this one, you can take a reference from the documentation here, from the hints. There is documentation on how to write constructor. But now is where I'm hoping that your recall value kind of comes into picture, that you already saw how a constructor would look like. It's a function, right? And remember that if you are writing a value, which is what it is asking you to do, that initialize the counter, you need to have a ref self as the first parameter. And then you will give an input value that you need to write. And you have to remember that it has to have a constructor annotation. Okay, so these are things we have already looked at in the slide. So this should be very easy now to write this very quickly. I'm going to give you 1 more minute for this, and then I'll start writing by myself. Okay, so I'm in step 3. I've already opened this one. This has some weird kind of, the zoom thing keeps coming for me. I'm trying to bring it down. Okay, nice. So I'm gonna write counter U32. I'll say constructor. Okay, function constructor, ref self, a contract state because I want to modify that. And then I have to take some input, right? It has to be U32. And I say self dot the name of the variable counter, and I have to write the new input into this. Perfect. Once I've completed, I can run scarp test. Oh my God, what have I done? Fail to get contract artifact for name equal to counter. Which file am I looking at? I think that's correct. If it expects me to also enable Sierra, check stored counter. Wait. I would have made some variable mistake. Counter, constructor, counter. Let's see. Okay. Make sure Stacknet target is correctly defined. It is defined. Maybe I should do the dependencies above. Wow. This is the magic of live coding. I have to debug live. Okay, let's see. Target Stacknet contract. Let's see if I am in the same. Yes, I am. Constructor, if done, that's correct. Let's see, contract address. And it should be fine. Okay, let's move to the next step. Even if it didn't compile for me, hopefully it has compiled and worked for you. So,
So what issue you having? I wasn't paying attention.
it says that for me, it says that I haven't defined the target correctly. It's failed to get the contract artifact for name is equal to counter.
Did you name the smart contract with capital C?
Yeah.
And what about the module? Like in the lib.cairo, is that?
It's correct only, but the file name is counter.cairo.
Right,
So
and that's the file name.
yeah.
But it's not saved. The file is not saved. I wonder if that has...
Maybe I have not saved it. That could be it.
The lib.cairo file is not saved.
Oh, I didn't make any changes to it, but I don't know. No, my counter.cairo was not saved, maybe. I don't know. Okay. Because in the previous one also it needed the counter. I mean, it needed the lib. So it found that and it did everything, I guess it was supposed to do. Okay. Yay, fun issues that we are encountering. Okay. So let's go to step 4. And in step 4, what we need to do is we need to now get to the more nitty-gritty things, that is implement an interface. Okay. So we need to write an interface which will give us the blueprint of the contract, and we are going to do it in steps. So for the first step, which is step 4, we are going to write the interface with just the get counter function. The get counter function should return the value of the stored counter variable within the contract. So remember that get counter is not going to modify the contract state. It's only going to read. So the way you have to define the function is in such a way that it takes this snapshot, right? And you need to implement the interface also. So you need to write the interface and you need to implement it. So let's look at the requirements. Implement an interface for a function named getCounter, which returns the value of the counter variable. The getCounter function must be within the contracts interface named iCounter. So you have to name the interface as iCounter you have to write the get count. You have to define the get counter inside the interface. And then you have to write an implementation which will implement this by just returning the value of the counter. You can take a look at the hints. But if you remember, every interface is defined as a trait. So you have to say trait iCounter and then have a generic variable. Inside that, you write your function, body of your, blueprint of your function, and put a StarkNet interface tag on top of it. Within your contract, you have to implement this so that that implementation can also have external access. So you have already seen the blueprint of how this would look like, and you can quickly code it out. So I'm going to do step 4 now. Okay, so first I will write a trait. So in order to say that this is a StarkNet interface, I have to mark it as an annotation. And my trait should be called iCounter. And I define a generic object T to tell me that this trait will be modifying or reading, writing to some type of variable, right? And the function that I have to define is called getCounter. Because I'm just going to read, I'm not going to modify, I'm going to take a snapshot of this T, right? Whatever that variable is, and I have to return this counter. So U32. Now I'm going to implement this, right? So this is a trait. I have to implement this trait. So now to implement it, the first thing I want to do is have it as a external. I should be able to call the function externally. So I have embedded this to be able to call it externally as version 0. Okay. So I say implementation, iCounter, IMPL. So this is a very standard way of writing implementation. So I'm just going to follow that. Off. Now I'm going to write super because this particular trait is outside the scope of this module. So I have to write super to be able to access this iCounter. And then on what am I going to implement this trait? I'm going to have a contract state, which I can read or write from. So now I need to implement the getCounter function. So function get_counter, right? Again, self and snapshot of the contract state because I'm not going to read anything. And I'm going to return a U32. So in order to return, I need to read the value of the counter. So I'll do self.counter.read. And I'm not putting any semicolon at the end because the way the functions work, the way return works in these functions is that if you don't put a semicolon, this becomes the last statement of your function. And if you don't put a semicolon, this automatically gets returned. So the last value that you write over here will automatically get returned. So similar to Rust. Okay, so I'm going to save this. Let's see if there are any other requirements. So to create a contract, you will need to define a trait with a name. The getCounter function should only be able to read the state of the contract and not modify it. Okay, let's check. Okay, let me save it properly. Okay, so once you have completed this, your test should pass. You can also, once the class is done, you can also take a look at what are the tests that, they have written. What are the tests that are written and what is happening in the background? What are we testing for? Small things, of course, but what is happening? Now we're going to go into step 5. So in step 5, we are going to have within the same interface, we have to write another function, which is increaseCounter that increments the current value by 1. Okay. So this is easy peasy now. It's getting easier because we are getting a hang of the language now. Right. So within the same interface, so within the same trait, I'm going to write the increaseCounter. Okay. And now I have to modify the value. So I'm going to take a reference to that, to this particular variable. And I just need to increment by 1. So I don't have to have any input. Okay. So I'm going to add this to the implementation. So I'm going to say self.counter.write. But what do I need to write? Before writing, I need to first read the variable value. So I say read and then +1 because I just need to increment it. So I'm not returning anything here. So I can close the statement by putting a semicolon, right? So the execution ends here. So I've added this increaseCounter, which was asked for in the step 5. And it should be within the contracts interface name iCounter, right? So I've done the same. I'm going to saving too many times. Okay. So start test and the tests have passed. Okay. Okay. So with step 6, what we are going to do is we are going to implement an event. Remember that whenever we are writing events in Cairo as a Stacknet contract, we have to have two parts to the event. One is the enum called event, which will define the event itself. And then the event is actually, which will declare the event. The event is defined as a struct. Okay. So remember two parts. So I'm going to go to step 6 now, which is the event, right? Step 6. Okay. I go to this and I say, now I want an event. So first thing I have to do is have this tag, which is event. Okay. And then the event has to derive some traits, as I mentioned. It has to derive the drop trait, that is, it can be deleted, and it should derive the Stacknet events trait. Event, I say events all the time. Okay. So this is how we know that this is an event. Okay. We need to have these parameters. And first we need to define an enum called event. Now they have asked us to define a specific event. So it is called counter increase. Okay, that's the name of our event. This is what it is checking for. Implement an event named counter increased. So I'm going to copy this name. I'm going to go back to my editor and I'm going to write. Okay. So this is the only event they've asked us to define. Now I have to define this event as a struct. So for that, I don't need this tag, but I still need this tag. This event needs to derive the traits. So I'm going to put this tag. This is the name of my event, name of my struct. And what should it emit? What is the value that I should emit? When defining the counter variable within the counter increase struct, okay, so the event should emit the current value of counter variable every time the value is increased. So what should I emit? When should I emit? Both are here. So I'm going to emit counter whose value is U32. We already know. And we have been asked to add a key so that the event is easier to index. Okay. So I'm going to add the key here. All right. So now I have created this event. Now they are also asking me to emit the event in the increase counter function once the counter value has been incremented. So I've not shown you how to emit the event, but you can just check it out here in the hint. It's already there, but it is very straightforward. You use self.emit, name of the event, and then the value that you want to emit. So let's go back. So in the after the counter has been increased, so self.emit, name of our event is counter increase, and the value we are emitting is counter, and the value of this variable is coming from self.counter.read. You have to read the current value now, right? We wrote an updated value. So we are reading that, we are assigning it to whatever needs to be emitted, and we are emitting this event. So every time we increase the counter, we will be able to emit this event. Okay, saving. Okay. So this is the step 6, and we have reached the main checkpoint, which is we have written a simple basic smart contract where we are able to get the counter value, increment the counter value by 1, and emit whenever the counter value is increased. So this is our first checkpoint.
Hey, let me step a little bit in and let me show you how you actually can deploy the smart contract that we created. So we worked for the first half, for the first part, and after that you can jump to the step 15, which basically it's from step 6 after you finish step 6, and below here you can actually reach the checkpoint. So you can go to the step 15, which is actually right down below here. And here we have all the necessary information to deploy our smart contract on testnet. So initially what you want to do first is actually check that your smart contract passes all the tests. So currently on my end, we are on step 6. We have our smart contract finished, implementing the event part. This is how it looks like. So we have the smart contract, we have the interface built, and then the contract itself with our storage, our event enum, our counter increase event, the constructor function, and then the implementation of our interface. Right now, I'm just running Scarp test to make sure I pass all the tests within this step. And now that we passed all the tests, we are ready to deploy the first part. So let me actually grab this command line. We will switch branches to step 15.js. And now you're passing the command in the terminal and then check out step 50.js. Now in your project structure, we'll notice a few additional things. In the script folder, we have this deploy TS and utils TS. And then we do have a package JSON and a package log JSON, but we'll get to that in a bit, right? So let's go back to step 15. The first thing that we'll have to do is install all the necessary dependencies. So with that, you have to install with npm install. To do that, go into your terminal and write npm install. And we managed to add all the dependency, and you'll notice that in your project structure, node modules have been created. Good. Now for the next part, we actually need to have a wallet created. So for those who do not have any wallet created, we'll go through these steps. And if you have a wallet created, what you'll have to do is just to get your private key and your public key. So to do this, let's go to step 1. So we'll have to create a wallet on StarkNet testnet using either Argent or Bravos extension. So for me, in this example, I'll use Argent. So I'll just get my Brave extension. I'll add this to my browser, and the same thing can go for the Bravos extension. You need to create a new wallet. So for this, you create a new wallet, and there's some things that your privacy policy, agree. You have to set up a strong password, press continue, and then here you can choose either a smart account or a standard account. Now the smart account comes with additional features that uses the account abstraction that we talked about in the previous sessions, but for the sake of this example, I'll use a standard account. But if you're interested into a more secured account with 2FA and other features, then you can investigate the smart accounts. Great. Now that I have finished, I'll go to my wallet itself, and we can see that we have already a wallet on the mainnet. Now, in our case, we'll have to switch to testnet. So we go to click here on mainnet, click to Sepolia, and then we'll create a new address, right? And we'll create a standard account. Now that I have my address created, it's time to, so I'll have to say my seed phrase. So in your, please do save your seed phrase. Make sure to have this in a safe location and don't share with anybody else. Now for our next step, make sure to copy your address from here, and then we'll have to request some funds in order to deploy a smart contract. So here you'll either be able to use the faucet that we have or a breach that you can transfer from layer 1 to layer 2. We go to the StarkNet faucet Sepolia. We'll add our address here, and then we'll request some ETH funds and make sure to pass the CAPTCHA challenge. I'll have to select all the motorcycles and finally send the request. You'll have to wait a few seconds here, and once the transaction has been verified and processed, you should be able to receive some ETH funds on your wallet. Great, our transaction has been successfully processed. You can access your account and you'll be able to see that you have received some ETH funds as well. Now, before going to the next step, we'll have to deploy our wallet manually. And to do this, you can go to your account. You click the 3 buttons here, and then you make sure to deploy the account. And then this ensures that our account is deployed on testnet. Great, now we successfully deployed our wallet. Give it a few seconds until the transaction has been confirmed. You can also check this button where you can see all the transaction, and you see account activation. You can click on it, and then you'll see that the transaction has been successful. Awesome. Now we're ready for the next step, where we create an env file. Now, going back, our next process or our next step is actually to create env file in our project structure. So to do this, you come here on your VS Code, and in the parent folder, you'll have to create an env file. Whenever you're working with env files, make sure that you add this in your git ignore, as we don't want to have our env file uploaded to GitHub, because this contains sensitive information and anybody can view it if the repository is public. Now for the next step, we'll have to export a private key from our funded wallet into our environment file. To do this, you'll go to your Argent account, click on your account, click on the 3 dots, and then click on export private key. Enter your password, and then copy the private key associated here. Make sure that you don't share this private key with anyone. Currently we're being on testnet, but still you'll have to follow good practices. Once you copied your private key, then you have to create a variable in your env file called deployer private key, and then followed by your private key from your wallet. Make sure to save the file. Next up, we'll have to export the public key of the funded wallet into our environment file. So I'll copy this. Here, I'll copy the public key. To do this, you'll go to your Argent account, you'll copy the public key, which is associated with this, and then you'll pass this in. Great. Now for the next part, we'll need an RPC endpoint. Whenever you want to communicate with the StarkNet network, either mainnet or testnet, you will need an RPC endpoint. In this example, we'll use the Blast API service, but there are many other great services out there. Now, we'll copy this line here, which is the RPC endpoint. It's the public endpoint for Sepolia testnet offered by Blast API, and we'll put it into our environment file. Now, we'll save our environment file and go back to our steps. As for the final part, we'll have to run the script that we have provided in the deploy TS. But initially, if you just finish the first half of the workshop, you'll have to change some parameters. As you remember, the first part, if we go back to our smart contract, in our constructor function, we just pass the value, and the full exercise contains additional parameters in the constructor function. So in our first part, we'll just have to modify this certain line, which can be found in the deploy TS. Let me show you. You go to scripts, deploy TS, and inside here, you will notice the constructor const. Here we will remove these two lines, as those are intended for the full exercise or the full workshop. And we will modify this initial counter variable to our actual variable, which is in our constructor function. And this is value. So value has to coincide to the value that you have here. If this has been named differently, so for example, increase counter, then you would have to name the variable increase counter here as well. Great. Make sure to save this. And now we're ready for the final step. The final step involves running npm run deploy. Now, before running the npm run deploy, a good practice is to first run scarp clean to ensure that all our builds are cleaned in our factory, and then run scarp build. This will compile your contract from the beginning and make sure that we are on the latest changes. Now we're ready to deploy our smart contract. To do this, run npm run deploy. Notice that our account has been successfully connected. Congratulations, you have successfully deployed your first smart contract. To actually check our smart contract on the Block Explorer, make sure to grab this address, copy, and then you can go to either StarkScan or Voyager to check the smart contract. Now, make sure to switch to Sepolia, and same thing goes for the Voyager. You switch to Sepolia. And please note that it may take a couple of minutes until the Block Explorer will index your smart contract. So if you deployed a couple of seconds ago and you pass the address, you may not notice your contract right away. Usually this involves that it takes a couple of minutes until this has been successfully indexed on StarkScan and Voyager. So be a little bit patient, and in a couple of minutes, you should be able to see your contract. Now let's see actually what we created. This is our smart contract that we have created. This smart contract has been built with the class version Cairo 2, and we can actually check our functions or our public functions in the read write contract. So we'll notice that we have the get counter. So in this case, I'll query this function, and you notice that our default is D. So to actually switch this to a readable format, we'll put decimals, and you'll notice that it's 100. Is the actual number that we have passed in the deploy. So you can see the value is 100 in this point. And now we have the write functions, which basically are able to modify the state of the contract. As you remember, whenever you want to modify the state of the contract, you have to pay a certain gas fee. For that, you'll have to connect a wallet. So we'll connect my ArgentX account. We'll go to increase counter, and then we'll write this. And you'll notice that this is a transaction that I will have to sign, and I'll confirm this. Great. Give it a couple of seconds for this to be processed. And then once ready, we'll go to the read tab, and we'll able to see if our get counter has been increased from 100 to 101. Let's check that. Let's go to a read. Let's go to get counter and let's query the function. As you notice, it's not D anymore, so we go to decimals and we'll see that's 101. Congratulations, you have successfully deployed the first part of the smart contract. Now, as for homework, you can continue the exercise and finish the second part and then redeploy the smart contract again. Thank you, and now back to you, Gian.
So by now you're able to write a basic smart contract. So you can take a quick look at the smart contract as well. We wrote the module first with the simple storage. Then we added the counter and the constructor as well. The constructor is writing an initial value to this, whatever we are sending while deploying the contract. And then we have two functions that we have implemented, get counter and increase counter. So get counter is getting the current value of the counter and increase is incrementing by 1. And every time we are incrementing, we are emitting an event called counter increased, and we are emitting the value of that counter. So, and for the implementation, I mean, we have written an interface which is being implemented. So this is like a simple smart contract. You know all the steps now to write the smart contract. And one of my small pro tips for you, like whenever you try to learn a new language, is that follow the process of read, write, test. Spend a lot of time in the beginning reading different types of contracts. Like don't put too much stress on yourself, like that you are not understanding the contract. Just read through lots of different Cairo contracts. Just look at the code. That's why, and when you look at something, right, when you start writing it, the recall value will be there. Otherwise, when you're starting to write programs in a new programming language, you won't know how to debug and where even the minutest of the things went wrong. But if you read a lot of code, right, it's not an advice that somebody generally gives to read code, but it worked really well for me. It works really well for me whenever I learn a new programming language. So just blindly spend 2-3 days reading from simplest to complex contracts, and you'll find lot of smart contracts, Cairo contracts online. Just read them, right? Just read and familiarize yourself with the pattern of this programming language. Once you're familiar with the pattern, then start again writing small to complex smart contracts, and then go for testing as to whether your logic is correct or not, local testing, and then go for deploying on-chain and on-chain testing. So this should be the process that you should follow. Like this is a very effective method of learning, and something very useful when it comes to like programming languages, especially to understand what the pattern of a programming language.
So the last thing as we wrap up are the resources. So you can see that you can use ASDF to install your dependencies. Scarb is of course super important. So make sure that you have that installed. Make sure that whenever you're working with Scarb, you're checking the versions of Scarb, and Scarb also gives you the version of your Cairo itself. So ensure that you're working on the most recent stable version, because that's when you will be able to access the best features. Foundry, we also have Foundry Toolkit for writing test cases, writing tests, and it's super cool. So definitely start exploring that. And then of course we have an extension, which is a VS Code extension that helps increase the readability of your code itself. For documentation, we have the Cairo book, which is all about Cairo. So if you want to get started with Cairo, this is the best place to go. In Starknet book, you can find everything that you need to learn about Starknet, the different components of Starknet, the theory behind them, as well as some practical examples on contracts. You have the Starknet Foundry tutorials where you can read about right from setting up to writing test cases, different types of test cases you can find on the Foundry documentation. And of course, for the CLI, you can find more information on the Starknet book. Starknet by example, created by the Voyager team, is again a brilliant resource where you'll find a lot of examples on different contracts. For example, cross contract calls or complex calls. All of this you can find in the Starknet by example book. And then Cairo by example has a similar approach, but for Cairo codes. Okay, if you're a beginner, definitely do Starklings. It's one of the most fun exercises and you will have a great time. It's very gamified. So as you keep doing, you kind of keep progressing to the next level. So very interesting. Again, if you want to step after Starklinks, you want to step in the intermediate level, then you have Node Guardians. The quests on Node Guardians are amazing. Just the UI UX, just the experience is really great. And once you're ready, you can always start contributing to the open source repositories on OnlyDAS. This is a good way to also make some money, get some rewards on OnlyDAS by contributing to the Starknet open source projects. Thank you so much. Thanks for joining us. I hope you enjoyed learning about Cairo, and I hope that you're also able to complete the session and you took away a lot of learnings in terms of how Cairo smart contracts work, and you're ready to write your first Cairo smart contract. Amazing. Looking forward to seeing all of you. Thank you.